Thank you, Jim. Can you hear me?
Yes,
All right.
I can't see
Uh,
you, but I can hear you.
that's probably for the best. Nobody needs to see my insane hair. Uh, all right. So uh, I hope most of you know me. My name is Ushnish Sengupta. I work in the University of Cambridge with Professors Matthew Juniper and Carl Rasmussen. And the focus of my PhD is applying Bayesian machine learning tools to thermoacoustic instabilities. And I would say that my PhD was not really driven by a specific research question, but rather the general desire to forcibly shoehorn Bayesian machine learning to anywhere we could within the field of thermoacoustic instabilities. And so this is the framework that I like to think in when I'm thinking about applying machine learning tools to thermoacoustic instability. So what are the things that we can do as engineers to avoid these instabilities, right? The first thing and the best thing that we could do is we can have an accurate, good model of the system, and we optimize that model and hopefully end up with a stable combustor. So can Bayesian machine learning help us do that? That's one question. Okay, so let's say that we fail to do that, and there are still, even after our best design efforts, we still have some instabilities in some part of the operating parameter space, right? In that case, we have to control the engine such that we can avoid these unstable regions in the parameter space. And the question then is, can we use Bayesian machine learning to do that? And the third thing that I not really investigate is, high frequency active control, because let's say that you want to operate, you're very ambitious, you want to operate the engine even though it's in a condition where it's thermoacoustically unstable. So you could use something like active noise control, but the problem is that the actuators that you need to design to that can be very finicky, and so nobody actually does that outside of laboratory settings. Yep, so we won't be looking at that. Right, so most of you have heard this spiel before, but I will just recap the basics of Bayesian machine learning. So normal machine learning, so all of machine learning is, predicting some output y from some input x, yeah. And normally in normal machine learning, you have a point estimate for the right. So given some input x, you have some point estimate of the output. The thing about Bayesian machine learning is that it comes with uncertainties. So initially, when we have not observed any data at all, we have this vague prior about the functional relationship between x and y, right? So that's shown on the left. So that's our prior distribution. And after we observe some data points, so we see, you see those 6 red data points. After we have observed the 6 red data points, we can apply Bayes' rule to obtain the posterior over the parameters of your machine learning model. And you can obtain something like the picture to the right, where you have low uncertainty near the observed data points, but high uncertainty far away from the data points. So, when you stray too far from the training data set, the Bayesian machine learning essentially says, look, I don't know what the output should be. And that's a useful thing to have when you're, when you're operating jet engines and you're deploying machine learning models in such a high scenario. Yeah. So this is essentially how Bayesian machine learning works. This is a simple example of linear regression. Yeah, it's y equals to w1x plus w0. So we have 2 parameters in this model, and we can specify the simple Gaussian prior over these 2 parameters. So that's the top row, right? And we take, if you take samples from this prior, you can see that it produces all sorts of random lines, right? And okay, so in the second row, we're observing we have observed 1 data point, yeah, and you see that after we have observed this 1 data point, the prior has now changed to a posterior, and it has become more concentrated, and the samples from that posterior now pass pretty close to that 1 observed data point. And now in the third row, we have 2 data points that are observed, and now the posterior becomes even more concentrated, right? So we're even more sure about what W0 and W1 should be. So now the lines that the samples that you draw from that posterior are even more concentrated, and you have a pretty good idea now what the straight line should look like. Now, in the final row, we have observed a lot of data points, and now you have a lot of certainty about what that straight line should look like. So this is essentially, in a nutshell, the idea of Bayesian machine learning. Initially, you have no idea. As you observe more and more data, you get more certain. Right. So the tool that I have used the most in my research is called the Bayesian neural network. And idea is the same as in linear regression. So you have in a neural network thousands of parameters, and you can specify a prior distribution over those parameters. I'm sorry, the equation is somewhat shifted. I don't know why that happened. So you can specify a prior distribution, theta prior. And as you observe data points, you can apply Bayes' rule to find the posterior. The only problem is that unlike the linear regression case, there is no analytical solution to this. There is no analytical solution here, so we must resort to approximate inference techniques. And this is an example of an approximate inference technique. It's known as anchored ensembling. So on the top left of the picture, you see the prior distribution, right? And what the anchored ensembling technique does is that it trains an ensemble of neural networks. And what we do is that we anchor the parameters of that neural network to samples that we draw from the prior. Yeah. So we design this special loss function that anchors the parameters of the samples of the ensemble members to samples drawn from the prior. And there is this wonderful paper by Pierce et al. That shows that if you train the neural networks in this manner, and after you have trained the neural networks, you will obtain samples from the approximate posterior distribution. Yeah, and that's the thing that we wanted. And this technique is scalable, so you can train these neural networks in parallel. So it's extremely cheap and extremely fast to do this. Okay, so now we have our hammers, and now we're looking for nails, right? So we're looking for problems that we can solve using Bayesian machine learning. One important problem that arises in the context of thermoacoustics is parameter inference in models. Yeah, because we know that thermoacoustics is pathologically sensitive to model parameters. So pen and paper won't get you too far. After you have made a model, you need to calibrate the parameters of that model with real data, right? Otherwise, the model won't be quantitatively accurate. So, but the problem is that some models can be extremely expensive and complicated and nonlinear, which means that this calibration can be pretty hard and pretty expensive. But neural networks can help here. So what neural networks can do is neural networks can learn posterior over the parameters given some observational data, and which is a probability distribution, and the neural networks can learn to map from an observation to this probability distribution. This can be learned. So you can train the neural network on many simulations, and you can learn this distribution from those simulations. So there is a one-time cost that you have to pay initially, which is, so you have to make lots of simulations and you have to train the neural network. What one the neural network, you can infer parameters extremely fast. So I just give you an observation, tell me, these are the parameters that correspond to these observations, and you have uncertainties because it's a probability distribution. So we are looking here at the G equation, which, as many of you know, is a reduced order model of a flame. It models the response of the flame to acoustics, which is of course something that we need to do when we are constructing thermoacoustic models. And it's a very simple model that uses a level set formulation and propagates the G field forward in time. Yeah, and this model has 6 parameters that we don't really know a priori. So like the wave number, amplitude of the perturbation, Markstein length, parabolicity of the imposed velocity profile, Strouhal number, aspect ratio of the flame, and so on. So On the right, see an experimental flame video that I have taken in our lab. So this is a Bunsen flame that is excited by a loudspeaker, yeah? So a sinusoidal tone. On the left is a simulation of the G equation. So we need to find parameters of the G equation such that we can have a very close match between the simulation and the video that we observe from our high-speed camera. Yeah. And so there was Hans Yu lab had already suggested one method to solve this problem. It's a very simple technique, filtering technique known as ensemble Kalman filter. But the problem of the ensemble Kalman filter, you have to run lots of simulations in parallel. So if you want to assimilate a video of the flame, it takes a lot of time, and sometimes it converges to wrong estimates of the parameters. So it requires a lot of observations of the flame. It's expensive to simulate, and you can have bad results. So what we did is what I explained just previously, which is that we learned the p theta given z, right? So we learned how to map the observations to the posterior over the parameters. And how do we do that? We first we ran 4,000 simulations, and we created 2.3 million simulated flame observations, right, to train the neural network. And you can see that, with these we can train the neural network, and we can create a test data set. And at least on the simulated data set, we see that the neural network is predicting the parameters accurately. Yeah. Of course, here we actually know the parameters because we are generating the data set from the G equation ourselves. Okay, so how does this work then on real data? It actually works pretty well. So what you see here is, so of course we performed a lot of experiments. We changed the fuel composition of the Bunsen flame. We excited it at different frequencies and so on. And what you see here is a superimposition of the actual flame. The flame data is shown with black dots, and in red and blue we see the simulation that corresponds to the parameter that was predicted by the neural network. And we see that there is a pretty close correspondence between the G equation simulation and the video, which means that the neural network is doing an excellent job of predicting the G equation parameters from the flame videos. This is happening in real time. So once you train the neural network, this is actually instantaneous. It takes milliseconds to assimilate new data, which is wonderful. Right, so that's parameter inference, trying to make physical models more accurate by assimilating parameters. Another thing that we do, so let's say that we have a good model, right? But we need to optimize different parameters in that model. So let's say that we have a combustor. That combustor has many geometric parameters. So we need to design the combustor so that it is thermoacoustically stable, right? So we need to optimize our model such that our combustor becomes thermoacoustically stable. How do we do that? So we can make a model, so we can make a simulation of the Helmholtz equations, and we can try to stabilize all the modes of the Helmholtz equation, right? The normal way that we do this in the lab is that we use adjoint techniques, and adjoint techniques give you cheap evaluations of the gradient, and you can use these gradients to perform normal gradient descent, right? But the problem with normal gradient descent is that you can get in poor local optima, right? So you can have so there been a better result, but because you were using gradient descent, you got stuck. So an alternative approach could be to use Bayesian machine learning to perform global optimization, right? So in the pictures here, you see an example where we're trying to do that. So what Bayesian optimization tries to do is that it doesn't just look for the optimum. It also tries to evaluate the model at points where we have high uncertainty, right? So it tries to explore and exploit at the same time. It tries to balance exploration which is exploring places in the parameter space where we have high uncertainty. And it also tries to do exploitation, which is, honing in on good combinations of parameters. And we here use a technique known as derivative enhanced Gaussian processes. And the derivative enhanced part is cool because we can actually use the cheap gradients that we obtain already from their joint models, and we can use that to accelerate the Bayesian optimization even further. So if you don't use the derivative information, you will have a slower optimization. Yeah. But if you use the derivative information, you can hone in on the actual global optima much faster. So here you see an example. So this is a simple network model, but of course you can do this with much more complicated models. So you can see that on the top you have the initial design of this is a cross section of an annular cluster, and you see that if you make these small changes to the geometry of this annular combustor, you can actually stabilize most of the modes of the annular combustor. And this is of course a work in progress. We're still working on this, but it seems to be a very promising direction. Right. So that's modeling and optimization. We're as discussed, we will also look at avoid regions of instability. And how do you use Bayesian machine learning to forecast instabilities, right? So this is, of course, we are not the first people. We are not the first to look at it, of course. This has been quite a hot topic of research for nearly a decade now. And many people have suggested different measures for forecasting thermoacoustic instability. But the problem with many of these measures is that although they claim to be universal, when you apply them to a new combustor, especially a complicated combustor with lots of operating parameters, you find that these prognostics can be quite noisy. And if they're noisy, you can't actually rely on them to forecast their thermal stability accurately, right? And that's not very useful if that's really the case. So our idea here is, our hypothesis here is that we can use the spectrum of pressure recordings or optical recordings, and the spectrum we think is a fingerprint of the underlying combustor state. And so what we want to do is we want to feed the spectrum to a Bayesian neural network, and with that Bayesian neural network, we try to predict the stability of the system. Yeah. And we tested this idea out in the lab. Of course, many of you have heard this from me before. So in the lab, we have a little turbulent combustor, and we record the pressure signals from the turbulent combustor, and we use the spectrum of that turbulent combustor to predict how stable it is. We can also measure the stability of the combustor by exciting it with a sinusoidal pulse and measuring how long it takes for the pulse to decay. And so here we are predicting the decay timescales of the combustor, and you can see that the Bayesian neural network can do it accurately, and it can also do it with, and it can also provide you with uncertainties while it is doing that. And just because it's a neural network doesn't mean it's a black box. You can actually use a technique known as integrated gradients to see which input feature the prediction of the neural network is most sensitive to. So this is integrated gradients of global sensitivity analysis. And for example, you can see here for this sample, the first harmonic and the third harmonic of the spectrum of the pressure spectrum seems to be quite instrumental in predicting, in informing the prediction. Right. So that was that we did in the lab setting, but of course we wanted to know whether we could apply these tools to the real world, right? And we have collaborators in the German Aerospace Center, and they operate this 100 megawatt, very large rocket thrust chamber, which it's a liquid oxygen hydrogen rocket thrust chamber, and it displays thermoacoustic instabilities. Yeah. Interesting thing about it is it's equipped with high frequency pressure sensors. It's equipped with a photomultiplier, which measures. It's a proxy for the heat release rate at different points within the thrust chamber. And we also have thermocouples near the injectors and elsewhere to measure the temperature of the system at different points. And so, of course, we want to use these sensor signals to see whether we can forecast these like we could for the lab system. And yeah, so this is an example of an experimental run on the BKD rocket thrust chamber. You can see that they're varying with, this is a 60-second run, and they're varying the chamber pressure, they're varying the ratio of the oxidizer to fuel, and you can see there is this angry red here in the spectrogram, and also accompanied by very high amplitudes in the dynamic pressure signal. So that's when the thermoacoustic instability happens. So there is a particular point in the operating parameter space where the chamber is thermoacoustically unstable, and our challenges can be forecast that. Yeah. So the setting, the machine learning model that we use here it has to be slightly different, of course, because this is a dynamic experimental run. So what we do is we use as the input some state variable and the control signals. Yeah, the state variables could be, for example, it could be the spectrum of the pressure signals like we used before. It could be the spectrum of the OH chemiluminescence measurements that comes from the photomultipliers. It could be the temperatures. It could be the chamber pressure, and so on. Right. So we have a lot of choices because we have a lot of sensors with the state variable, and we can also use the control signal, which is which informs how we will vary the chamber pressure and the reactor oxidizer fuel ratio in the future, right? So, and what we want to do is we want the Bayesian neural network to predict whether the combustor will be stable 500 milliseconds from now. So we will use information, signal information from the present, and we want to predict 500 milliseconds in the future, because that's enough time for the controller to take evasive action if we do predict an instability. Yeah. Right. So we see that we trained many models, we evaluated many models, and we see in general that the models are actually pretty good. So let me explain this picture. The blue line actually, the blue line tells you when an instability actually occurred. So when it's 0, it means that it was stable. When it's 1, that means that an instability occurred, right? And the red line is our model, and our model is trying to predict the probability of the system remaining stable. Yeah. And using data from 500 milliseconds in the past. And you can see that the model actually does a pretty good job of forecasting the instabilities as and when they happen. Yeah, but of course, pretty good job is not enough. We are engineers. We need to quantify how good the models are, and how does the accuracy of the models depend on the choice of the state variables that we feed into the model, right? Jim, do you have
2 minutes over time?
Oh, sorry.
Continue.
Soon, I will hasten my pace. Sorry. All right. So we use a metric known as ROC. Machine learning people will be very familiar with the metric. This is essentially varying the threshold and computing the area under the curve for the true positive rate versus the false positive rate. Right. And evaluate all these models, and essentially what we see, so the naive baseline model is just predicting that the system stays in the same condition, right? So that's a stupid model. Any model that's useful must be much better than that naive baseline. Yeah. And we see that depending on the input, the accuracy of the model can vary. So if you use the static pressure, oxidizer fuel ratio, temperature, pressure of the injector, you obtain a pretty good AUC, 0.9908. But if you use more information, for example, the spectrum of the dynamic pressure signal, you can obtain even higher accuracy. So we see that in the final row, where we are using all the information, that's actually the best model. So that's might seem like a common sense thing, that using more information leads to a better model, but that's the conclusion that we can draw from here. We also did this thing with Rolls-Royce, and I don't really have time. I won't go into the details, but essentially it's similar to the experiments that we did in the lab. They have 2 operating parameters, and they have some data, and we want to predict the distance from the instability using pressure signals. So this rig only has pressure signals, no photomultipliers and so on. And it turns out that the machine learning models can also do that. So we can pretty accurately predict the distance from the threshold. And it also turns out that the exponent, permutation, entropy, and so on, they are, as we found in the lab, they are very noisy, and they're not very useful for predicting the actual threshold of the instability. Right. So, of course, I do have collaborations with other ESRs. I have not talked about their work because they will talk about their work in their own presentations. But of course, I'm collaborating with my lab mate, Francesco Garita, for Bayesian inference in Raiki tubes, and with Michael McCartney, who is also machine learning prognostics with his GE data and also with NTNU data. And finally, of course, we have also presented our work in different conferences, and we are preparing more and more journal papers and trying to wrap as we are wrapping up these projects. And if you're interested in this, please go to my Google Scholar. I have made all of these papers and most of the presentations. They're online. So yeah, thank you. Sorry for going over time.
No problem, Ushnish. Can you maybe also share the papers with Bridget?
Yeah,